Greetings everyone. In this video, I will demonstrate our research on cognitive load estimations and also discuss some applications for XR systems developed at our lab. Part of the presentation will be done by Dr. Omkar Shah, who is a gold medalist from AIIMS New Delhi and presently a postgraduate trainee at the same institute. Myself, an associate professor at Department of Design and Manufacturing and also at Center for Cyber Physical Systems at Indian Institute of Science, Bangalore, India. I also work on standardization and presently a vice chairman of International Telecommunication Union Study Group 9 and also a co-chair of the Interlocutor Group of Audiovisual Media Accessibility. I also a convener of BIS panel on metaverse. Earlier, I studied computer science from University of Cambridge Computer Laboratory and also worked there 6 years. As part of my postdoctoral research, I worked with Jaguar Land Rover, British Aerospace Systems, and also Technicolor. I set up Intelligent Inclusive Interaction Design Lab at IISc in 2016 after returning from Cambridge. Presently, we work on these 6 verticals, namely aviation, automotive, assistive, extended reality, robotics, and Industry 4. Often these verticals combine with each other and we have mix and match applications. And the present demonstration and presentation will be rather more a horizontal activity as the research on human factors tie together all the verticals together. This is a quick recapitulation or balance sheet of our lab. So during the past 8 years, we were uh, moderately successful in terms of getting funding from both government funding agencies as well as various industries. And we also have 7 PhD students already graduated and 2 more submitted in the recent time. And also our research was covered by various media outlets during the past 8 years. So in this slide, I am just presenting 4 videos rather quickly to show the gamut of our applications. On the top left is a virtual flight simulator, and here you can see that we are running the same software as a desktop flight simulator as well as a virtual reality simulator, showing that how the rendering technology can change the way we view a flight simulator. And we developed the system to estimate cognitive load of pilots. Top right is our latest work with Group Captain Ajit Krishnan, one of the 4 astronaut designates of India, and we developed a spacecraft simulator and compared various human-machine interfaces of existing and future spacecraft. You may also see I'm donning a VR headset and a EEG device. Bottom left is one of our collaborative work with Collins Aerospace Systems, and we developed a mixed reality-based system for helping workers to manually assemble various machine parts. And bottom right is our work with students with severe speech and motor impairment. We took an ambitious approach to teach them operating robotic devices. And we deployed a system by which they can do a simple block printing task for their rehabilitation as well as educational effort. Now, seemingly, these 4 different case studies are again tied together by our research on human factors and cognitive load estimation, because in all of these use cases, we tried various means to understand the human factors, and cognitive load estimation was one of the main way of quantifying both subjectively and objectively the acceptability or user performance about the system. So in the next few slides, we will further elaborate on the topics of this cognitive load estimation. So if you look at the Wikipedia article on cognitive load, that it has a very simple definition, one-line definition. And this cognitive load word was first uttered by this gentleman, George Armitage Miller, And it has also been championed by John Sweller. He is from Australia and mostly explored cognitive load among students. And cognitive load is it among psychologists, it does not have a single definition, but it is related to the finite capacity of working memory that we just discussed. Mental workload, that if I ask you to do many things, you will have more mental load. That if I, like our memory game, if I want to remember two words, you will have more mental workload than if I want to remember only one word. And then based on our activity, the stress, distraction, boredom, all these has effect on the cognitive load. And why it is important, or why we are working on it, and in particular, this is a press release from BBC, a mind reading combat jet for the future. So it's a UK STEM set program who are already working on assessing cognitive load of pilots, and the automotive community even one step further. They already even deployed some system for distraction detection, and we are also involved in a similar project with some many automotive industries. You will see examples, and this is also a screenshot of a press release by New Scientist in 2020 when they interviewed me for know about our work on eye tracking for pilots. But unfortunately, we did not disclose a lot of detail, but still they opted for covering that in New Scientist. So interestingly, analyzing cognitive load or affective state from ocular, that means eye-related parameters, it dates back to the days of Charles Darwin. So this is one book of Charles Darwin. So all of we know about him, about the theories of evolution or natural selection. But he did interesting work on analyzing how people's pupil dilates or how their expression changes, and that has been captured through their eyes. And later on in 1950s, this book, I have a copy of the later book called The Telltale Eyes. It recorded pupil dilations when they show provocative and non-provocative pictures. And also it recorded pupil dilation across cross-gender and also in different situations. And this is the picture of a very early stage eye tracking device, which has been used because in 1950s, there was no electronic eye gaze tracker. And in next lecture, we will discuss further details about eye tracking and how we detect cognitive load. Many times, unlike other parameters, cognitive load we do not measure, we rather estimate. And this estimation is often based on correlation analysis. That means we set up a task where we know that one condition will exert more mental workload than the previous condition. On the top right, you can see the picture of this n-back test, where I know that a 2-back test will exert more workload on you than a 1-back test. Or we created situations or tasks where we already assume or where we know that a certain section of the task is more difficult than other tasks. Say when I am driving, maybe parking the car in a congested parking is more require more precision or workload from me than driving on a freeway. In aviation community, they use a term called low gain task and high gain task, like landing an aircraft is a high gain task, while making a free fly with autopilot may be a low gain task. And we created such situations in either simulation or in laboratory and compare set of physiological parameters across these different tasks and try to see their correlation. So that's why we use the term estimation in terms of measurement. And as we discussed in the previous cases, so here we are talking about task in the 10th of second to the fraction of 10th of seconds based on the time scale of human action. We are talking at this cognitive band. So this is from a dissertation that which reported how different ocular parameters they are affected by cognitive load. So upper arrow means increasing, lower arrow means decreasing, and they represented this blink duration. This is endogenous blink, that means automatic blinks. Saccade amplitude, we discussed about saccade in the previous class in terms of the distance travel between two fixations. Fixation duration, that means how long you are looking at something. Frequency, how many times you are changing fixation within a unit time. and so on, area of visual field, etc. So next we will discuss about that how we can use EEG for cognitive load estimation. And in the last few days, or rather last few months, Omkar was doing some interesting work on analyzing EEG for estimating cognitive load. So I am handing over to Omkar for discussing this part of the lecture.
Okay, so before we talk about EEG, again, this is a schematic diagram of the brain and the various areas. So different areas in the brain are responsible for different functions. We all know that. So basically, you can divide them into lobes. So we have the frontal lobe, which is the front part of the brain. We have a parietal lobe, which is on top of the brain. We have an occipital lobe, which is the back. And then we have temporal lobes at the side. A broad generalization and simplification will be the temporal lobe is mainly responsible for auditory processing. The occipital is mainly responsible for visual processing. Frontal area is mainly your higher order tasks like judgment, task solving, problem solving. And parietal area is mainly responsible for motor movements, planning, and integration of all the three areas. You can see in this image afterwards, you can Google also and see which area is corresponding to what function. And here you can see superimposed on this are various electrodes. So these electrodes are basically how we measure brain activity using EEG. So EEG stands for electroencephalography. You must have heard of ECG, which is most commonly done, which is electrocardiography. So basically, the heart has only one circuit, so it is very easy to analyze an ECG. But if you look at an EEG, this is the signal that we get. So it is a very like it is in 1924, Hans Berger recorded the first human EEG. So we consider him as the father. So EEG analysis is very complicated. It is still undergoing development. So how we measure EEG is through scalp electrodes. As you can see over here, an array of electrodes are applied to the scalp from which we measure potentials. And each electrode, the recording is what we see. So again, talking about the basic physiology, we know that this is a neuron. You must be aware. Neuron is under in a state. Okay, so each cell has a cell membrane in which there is a potential outside and potential inside. How we measure potential is we measure the inside potential with respect to the outside. So in a resting neuron which is not firing, I'll just get the pointer. Okay. In a resting neuron which is not firing, you see that there is negative 70 millivolts. This is a depolarized state. The cell is at rest. So it is negative 70 millivolts inside with compared to the outside. So this is maintained by sodium potassium pumps, which pump 3 sodium outside and take 2 potassium inside, leaving a relative negativity inside. When there is a stimulus is presented to this neuron, it undergoes something known as depolarization, in which sodium channels are opened and there is an influx of sodium which comes in, which increases, and now there is an increased positive inside. So this is now the voltage will increase to approach 30 millivolts, following which there is something known as repolarization and hyperpolarization. So in hyperpolarization, the potassium channels open and there is a efflux of potassium from the cell, which leads to a relative negative potential. This requires a threshold. If the stimulus is above this threshold, only this action potential will be generated. And this hyperpolarization occurs so that there is a gap between two stimulus, so that the neuron is not continuously firing. It will require some time before it reaches back to this threshold. So what EEG measures is a summated activity because there is a very complex organization of neurons. We can't measure each neuron depolarizing and each neuron repolarizing. So about thousands and thousands of neurons or millions of neurons, when they fire together, that is what we measure as EEG. I explained about resting potential, action potential. Okay, so now as you see, these neurons, basically the cortical neurons are arranged parallel to the surface. So when there is a neuron firing, like let's say this area has started undergoing depolarization. So there is a generation of a dipole because this will be relatively negative. and this will be relatively positive. So basically EEG is measuring the dipoles that are being generated. Okay, so now when there is an activation of a neuron, we see that the inside potential has become positive. There's a depolarization when the neuron is activated. However, there will be a relatively negative charge outside. So this is what the surface electrode picks up. However, this depends on where the neuron is located. If it is a surface neuron and that is getting activated, it will generate a negative over here, which the electrode will pick up. However, if a deeper neuron is getting activated, there will be a relative positive at the surface. So the electrode will pick up a positive signal. So we have to be aware of these factors, that positive on an EEG doesn't mean that there is a depolarization which is occurring. It could be a hyperpolarization also, which is occurring, but it is deeper. So there's a relative difference in the dipole generation. Again, to more complicate this matter, by convention, an upgoing signal in the EEG is classified as negative, and the positive signal is downgoing. So that is just convention. And okay, so this is when we are considering one neuron. When we are considering other neurons, there are certain neurotransmitters which might increase the threshold or decrease the threshold of the next neuron by generating what are called postsynaptic potentials. There are two types, excitatory and inhibitory. So that is basically mediated by the chemical messengers between two neurons. So that again is picked up by the electron. Okay, coming to some technical components. What we follow in EEG is something known as a 10-20 system, which gives a standardized placement of electrodes around the head. So we basically measure the nasion, which is the bony prominence in between your eyebrows. We measure the inion, which is the protuberance at the back of your head, you can see. And this is divided into 10%, 20%, 20%, 20%, 20%, 10%. So all electrodes are placed like this. So we get a generalized electrode and a constant electrode placement irrespective of individual head size. Montage is basically how we are going to analyze these electrodes, so how we connect these electrodes. The most common montage used is this bipolar montage, where we compare the voltage changes in this electrode with this electrode, with this electrode. So this generates a chain, which is called as a bipolar montage. Okay, the nomenclature of the electrodes is based on the position of the position on overlying which brain area they are. So F stands for frontal, over the frontal lobe. C stands for central, P is parietal, T is temporal, O is occipital. The numbering is such that all even numbers are on the right side, all all odd numbers on the left side, and Z stands for central, which is the central electrodes. So most commonly in medical use, when you are analyzing the morphology of EEG for CGR analysis, we use something known as a bipolar montage, because it is, okay, I won't go into the detail of that, but it is easier to screen for epileptic abnormalities. However, there is something known as an end of chain problem which occurs, because this electrode doesn't have any reference electrode in front of it, and this electrode doesn't have a reference electrode behind it. So to overcome that, we have certain circumferential montage where FP2 will be compared to F8 to T4 to T6, and then we compare electrodes like this. So basically that changes the morphology of what we are seeing. So we change our interpretation that way only. There is no standard interpretation of an EEG. Most commonly when we are doing when we are using quantitative analysis, we use something known as referential montages, where all electrodes are compared to a certain average. The average is usually taken as your auricle, which has no electrical activity of its own. Then there are certain concepts of, there are technical components of page speed, filters, and sensitivity. So page speed is basically how fast your EEG recording will go. So if the page speed is very fast, all the recordings will be clumped together. And if it is, but you will get an increase in amplitude. And if you decrease the page speed, you'll have a stretched out signal for analysis of briefer details. Filters are basically to filter out, we have high pass filters, low pass filters, and notch filters. So the EEG signal is in microvolts. So it is affected by a wide variety of other stimulus. The line noise in the room will affect the signal. Muscle movements will affect, eye movements will affect. The generation of your the ECG, the cardiac cycle will also affect. So for that, to remove those effects, we use filters. And sensitivity is basically how much you want the machine to record up for a particular amplitude. So if you increase the sensitivity for a small voltage, it will show large deflection. If you and vice versa, if you decrease sensitivity. So in an EEG signal, when you look at it, there are three attributes to it. One is the frequency, which is how many oscillations in a second. Second is the amplitude, how much is it deviating from the mean. And third is the morphology, it's like what is the overall shape uh, of the EEG wave. So as an oversimplification, usually in biological EEG signals, as the frequency increases, the amplitude decreases. Because as you remember, EEG measures summated activity. If there are a large number of neurons firing all over the place, the overall summated activity will decrease because the dipoles will be oriented in different directions. And morphology analysis, basically what we do in medical, where we identify seizure potentials or we look at certain various activity which is different in particular brain regions. Okay, so now coming to PSG stands for power spectral density, which is what we are working on in this project with Sir. So basically, each frequency bandwidths over the years have been classified based on experiments. So the earliest experiment was by Hans Berger, was he discovered the alpha wave. So when you close your eyes and you are in a resting state, what EEG activity is generated is called an alpha wave. It has a frequency of 8 to 13 hertz, and this is the correlation that was gathered from it. So if you give a person a mental task, we see that the frequency increases, the amplitude decreases, and 13 to 30 has been classified as beta. So here you in sleep wave, we have very less neuron firing. So you can see the frequency is very slow, but the amplitude is much higher. So these are the frequency bands which have been classified now, and we have correlates to what each band means. So you might have seen some videos on alpha wave stimulation for deep sleep and all that. So this is what they're talking about. Okay, so now I was saying these all activities can cause artifacts in the EEG recording. So here you can see this. Um, Anyone can guess what this artifact is. You can see it stopped after this point. Present only over here, occurring at frequent intervals, occurring only at the front electrodes, not at the back electrodes. So this artifact is generated due to eye blinks. Every time the eye is blinking, eye also can be, because of the charge of the retina, it is can be approximated to a dipole in which the positive is in front and the negative is behind. So moment when you blink your eyes, your eyeball moves upwards. The eyelid comes down, the eyeball moves upwards. So there is a positive going towards the front electrodes. So you can see this big downward deflection because downward is positive in EEG. So these are eye blinks. So for EEG analysis, it's important to remove these artifacts. Eye blinks can be basically removed by asking the patient to close the eyes. So over here, you see the patient has closed the eyes, there's no more artifact. However, there are softwares which can analyze and exclude these eye blinks because we know exactly how they look. Uh, mo Movement artifacts are due to movement of the head. Muscle artifacts are very high frequency, so we put a low pass filter to remove those. And sweat artifacts have very low frequency, so we put a high pass filter and remove those. There are commercial software which can do this analysis and remove these artifacts. However, if you are writing your own code for analyzing each, then you have to make sure that you are accounting for these artifacts. So EEG analysis, a quantitative analysis of EEG mainly we use. So that can be divided into three main categories. Changes over time, event-locked events, and 3D image modeling. So talking about changes over time, we use this for tasks which have a specific duration. Like we have, say, in ours, we had a pilot simulator. So the person is flying an aircraft in a simulator, and we are observing changes over time that is occurring in this person. So one analysis is traditional band analysis. We look, okay, the beta wave is there, alpha wave is not there, so it means this. That is what we do in traditional bands. Then from traditional bands, you can calculate the power spectral densities, which will tell you how much beta is there, in which area it is there, and quantitative measurement of that. Then we can do a topographic mapping, like if beta is increasing in the occipital lobe, I know the person, means I can correlate that there is more visual processing that is occurring in this person. Event locked events basically have a single event. So an image will be flashed before you and it will close. And then we see what is the change that has occurred. These are the event related potentials. 3D image modeling uses something called as inverse problem. So what we do in that is using information from all the electrodes, we calculate which dipole could have generated such an influence on all the electrodes. So these are two softwares, Loretta and S Loretta. So they give you an image modeling. So like how an MRI generates an image. So we're using EEG, we can also generate images to show which area of the brain is getting activated in that part. Coherence and phase related analysis is again based on the assumption that if two EEG signals are in sync with each other, the brain areas are more likely to be correlated and functioning together. So this is mainly used in functional analysis. So which brain areas are working together, which brain areas are not working together. So talking about power spectral density. So this is basically the tool we are using for estimating cognitive load. It is an established feature. You probably know more about it, but what we do is basically we apply a Fourier transform to get the individual spectral components of it. And we use Welch method because they are also differing in time. And basically Welch method applies the Fourier transform to small windows that are created. Then we take this and we put it into the bands we have already defined, like beta is 8 to 20 and 8 to 14 and alpha is 4 to 8. So then we put it in the frequency bands and then we know which component frequencies are involved in that particular signal. Again, there are commercial software which will do all this, but you can write code to do it on your own also. Talking about cognitive load, sir had already explained what is the concept of cognitive load. So when we talk about cognitive load, we are basically there's a depletion of your mental resources due to the tasks that are there. High workload and low workload both have their pitfalls. So in low workload, you are more likely not to be vigilant. You're more likely to make errors if your workload is not high. Because high workload can lead to fatigue and you may take wrong decisions. You may fail to integrate proper information. This, however, is a highly individualized concept. Somebody like taking an example of a doctor who works in an ICU, he probably has a much more tolerance for workload than if you just enter and you are bombarded with all the decisions he has to make. So again, it is individualized to the person and to the state. If you just wake up in the morning and you're given a big integral and differential equation to solve, you probably get very stressed. But however, in an exam, you're already prepared, you're already in a prepared state of mind. So cognitive load won't be that much. So classically, cognitive load has been used in air traffic controllers and healthcare workers who have to take correct decisions in with high workload conditions, and it's very important. Decision can lead to loss of life. So this is basically the research which has established. So we are trying to use this research to our experiments. So this is some of the things that occur during which increase your mental workload. You have to integrate your task related knowledge, your working memory, your decision making, and you have to pay attention to what is going on. Again, cognitive load theory, sir mentioned that it basically involves the working memory, which is responsible for converting your sensory to long-term memory. So everything that you perceive in your brain from your sensory memory, your brain makes a decision whether you have to retain it. So in case you get an OTP, you remember it for like 20 seconds, but you remember it. If I ask you after 20 seconds, you won't remember it because your brain has made a decision that this is no longer relevant to me. So I'll forget it. So, and it also puts it into long-term memory, which is called schema. Your brain has a schema is basically like concepts. So you have learned concepts as you have studied and have you have learned how the world works. So basically everything you learn is put into a schema. So there are three types of cognitive load, intrinsic, extrinsic, and germane. Intrinsic is basically the load that is generated by the task itself. So learning ABCD versus learning integration or learning differential. So that is the intrinsic load of it. Extrinsic is how we are presenting. If I put more videos and I put more animations, you'll probably learn better with a lesser cognitive load. Whereas if it is just text, you will probably have more cognitive load to learn that. German cognitive load is when you don't have a schema for a particular thing. When you're learning a new concept for the very first time, like let's say riding a bicycle or something. For the very first time, you have no schema in your brain of how this is supposed to work. So that is the third concept of cognitive load. So how do we assess cognitive load? Is we have subjective and objective metrics. So NASA TLX is one of the gold standard subjective tools that is there, NASA Task Load Index. So basically, there is a set questionnaire, which at the end of the task, the pilot will say, okay, how much load I felt, how stressed I was, and basically there are 6 to 7 domains in that. But one of the disadvantage of this is after the task is over. So you might have had periods in which your load was higher or load was lesser, but at the end of it, what you will remember is basically only some part of it. There's a lot of information lost. So then we have this air traffic controller ATWIT, which at every simulation there is a freeze point, and the question is asked, what is your load right now? Then again the simulation will play, again it will be freeze. So using these freeze points, we get data from the entire simulation. But as you know, subjective metrics are they are likely to be influenced by the person. There might be incorrect reporting. So we go for objective measures. So objective measures we can divide into behavioral, physiological, and neuropsychological. Behavioral estimates of cognitive load, some are mentioned here, but for example, I can assess that how much cognitive load is there based on how much, because some people have started doodling, some people are shifting in their position, some people are moving their legs. So these are the behavioral. So I can estimate that the cognitive load is increasing. Physiological, like how Sir said, blink frequency, pupil dilation, ECG, heart rate. If you're more stressed, your heart rate will increase, your pupils will dilate, basically due to activation of the autonomic nervous system. But this physiological again can be influenced by your body. Like suppose for pilots, especially who are doing high G maneuvers, their heart is already stressed due to that, and because of the load they're experiencing, in order to maintain blood pressure, their heart rate will increase irrespective of what their cognitive load is at that time. So that is why we use neuropsychological measures. EEG is one, and then we have fMRI, which basically fMRI and FNIRS basically measure the vascularity in certain brain regions. So it is based on the assumption that if there is increased blood flow to a particular brain area, that brain you're using that brain area more. Whereas EEG uses electrical signals. So again, this is basically the most established research is based on beta, alpha, and theta bands. We have because the gamma and mu bands are recent developments. So using correlation experiments, we have understood what each band most probably estimates in the brain. Like for theta band, increase in theta band has shown theta band is shown to increase with increased fatigue, increased workload, increased demands, concentration, decreased mental vigilance. Similarly, alpha. Alpha is inversely related. Increase in alpha wave is seen when there's reduction in attention, because as you remember, alpha wave comes when you close your eyes and you're just sitting in a relaxed state. Beta band is related to visual attention, working memory, working load. And basically, beta band is concerned with the visual system. So in tasks that increase your cognitive load but don't increase your visual attention, beta band won't increase, but theta will increase. In visually demanding tasks, theta and beta both will increase. So again, this is a very good summary from this paper by Rojas. You can see he has given a comparison of all the indices that have been developed over the years and what they correspond to. So you can have this for reference later. I won't go in detail. Okay, now coming to two important concepts, which initially were considered similar, but now there are two different constructs basically. There's cognitive load and there's task engagement. So for example, increasing task difficulty increases the load and increases the engagement. But this is true only to a certain point. After some time, if the load continues to increase, the engagement starts decreasing. Like for the earlier presentation I took on the visual system, as the concepts became more and more tougher, the load kept on increasing. But after a time, the engagement dropped off. So cognitive load basically is measuring the working memory, whereas engagement is basically measuring the attention. Are you paying attention to the task? So here you can see 4 states in which there is high cognitive load and high engagement. There is optimal functioning till a point beyond which there will be burnout, and beyond which there will be burnout. If there is high cognitive load and there is low engagement, the vigilance will drop and there will be inattentiveness. Similarly, if there's high engagement but there's no load, there will be minimal executive function because it's not really interesting to you. You're paying attention, but this is underutilization of your task. Like if I start teaching you ABCD with a song and dance, you'll very be engaged, but there's no cognitive load. And if both are low, obviously there'll be poor functioning. So why this is important to us is basically task engagement has been used in designing adaptive systems. So in case the vigilance starts if the engagement starts dropping of the person, the task shifts from an automated to a manual operation. So the person starts interacting. However, if his cognitive load has now started increasing, it will switch the system back from manual to automatic to maintain the operator in a optimal state of functioning. So what we are doing is we are basically using this task load index. Again, a lot of research has gone into this, and basically we are using an index which is theta by alpha. So we know that with workload theta increases, and we know that with workload alpha decreases. So we are basically using this index to measure the cognitive workload of pilots or operators to measure how and to what we were comparing is AR, MR, and VR. So which is having a higher cognitive workload, we are measuring using task load index. Again, this is called the brain beat by Holmes. So and basically theta increases with increasing task difficulty. And as you remember, processing, task solving is done by the frontal areas. So we are using the frontal theta activity and we're using the parietal alpha activity. Again, you can see it has been many studies have gone into it showing a correlation with all these factors like fatigue, workload, difficulty, working memory. And the other thing that we are measuring is engagement. So as I said, engagement basically measures your ability to have a sustained attention to a task. So again, this was used by Pope in his experiment in 1995. So where they designed an adaptive system, and Freeman also developed this work. So a lot of indices were put forth, and a lot of montages are used, and there are various comparison studies also done. So basically, we were also using and seeing which montage will give us a better result, show more correlation, and which index will be better reflective of engagement. And as you can see, this engagement index has basically been developed in education field because we want students to be engaged. We don't want the lectures to get boring. And basically in gaming, we want people to get addicted to it. Like if you increase the difficulty of a level, the person is more engaged. But if you make it very difficult, you'll get frustrated and you'll just leave the game. So this was the initial development. And this has also been applied to automobile machinery and missiles. So missile controllers have to be engaged and have with a optimal cognitive load. If they are not engaged, they may fire a wrong missile or they may not fire the missile on time. So this is basically what we are working on. So in our experiment, we had pilots who were undergoing a simulation with different scenarios. In one, there's a helicopter which you have to shoot down. In other, you have to shoot down a Mach 3 fighter jet. So what we saw was, although the cognitive load was increasing, after a point, the engagement of the pilots began to decrease. So that is what we are trying to work on as to why the engagement is decreasing, what effects this can have. If engagement is decreasing, it means that the pilot is no longer vigilant. So he may be tracking that one plane going at Mach 6, but he may not notice that there are three more enemy aircraft that are come on his tail. So that is what we are working on right.
So after discussing the theories of cognitive load estimation from ocular parameters or EEG parameters, now we will briefly go through a few applications to show that how we use these cognitive load estimation techniques. Now you can always question our findings, and we encourage that or we welcome that because the present evaluation or development was constrained by the present availability of technology or devices. But still, we will quickly go through a few applications and devices to give you an idea that how you can use the existing cognitive load estimation theories for extended reality application comparisons or evaluation. So we set up lab with the following set of devices. So for augmented reality system, we used a video see-through interface. And for mixed reality, we use the Microsoft HoloLens. For virtual reality, we use HTC Vive Pro Y, which has integrated eye tracker. HoloLens also have integrated eye tracker, although the specification is different from the one available with HTC Vive Pro Y. And for screen-based system, we used a Tobii Pro X3 120 eye tracker. We also used motion capture systems, specifically the OptiTrack Flex 13 system to measure hand movements, and also used a 32 channel EEG device and the analysis already presented by Omkar for comparing different extended reality applications. To start with, first we developed a sensor dashboard, which is somehow related to Industry 4 applications. And we evaluated 2D graphs rendered on 2D media, that screen, then 3D graphs rendered on 2D display, and also 3D graph rendered on 3D display. Now, in all these upcoming slides, if you would like to have further details, you can look at the bottom of the slides where I put a reference to our research paper. So without going into much details of our findings, we mostly reported a speed accuracy trade-off, means that users were more accurate when 3D graphs are rendered in 3D media, but they were faster in response when the similar graphs are displayed on a 2D screen. We developed a 3D equivalent to Fitts law task, or the ISO 9241 pointing task. So just to give you a brief intro, so Fitts law task was, or it was published as a paper in the Journal of Experimental Psychology in mid-50s by Paul M. Fitts, and later in 1979 Stuart Curd used the same law to predict to Xerox PARC that mouse is going to be the fastest computing device, and from then onwards it becomes a ergonomic or ISO standard for evaluating any pointing device. So we developed a Fitts law ISO 9241 pointing task in 3D, and we found that the users, of course, most fastest or having least cognitive load with 2D display or video see-through display, and their physiological parameter indicating cognitive load is higher for mixed reality system. Next, we developed, along with the senior engineer from Faurecia or Forvia, as a external research program sort of collaboration, uh, VR and MR implementation of welding tasks. So here you can see that one user, he is doing spot welding, where he is setting up parameters in a VR interface, and the whole system was integrated to an actual welding probe which is doing the same spot welding. And we also developed system for arc welding process using both virtual and mixed reality system. So very soon you will see the mixed reality implementation for our arc welding process. And during experiment, we used a smaller desktop robot to keep the whole system safe. And for the same task of arc welding, we compared VR and MR interface. And again, we found that the VR interface was easier to use and showing less value for the parameters indicating cognitive load. So here the robot is following the same path drawn by the finger of the user, just shown before. Next, we undertook another study where we compared the takeover request for a semi-autonomous vehicle. So here the vehicle was equipped with a camera and it can see the lane marking. But then we created holograms or virtual obstacles coming on its way, and also other traffic participants. And the user has to take over the driving himself, also at the fork of the junction. And we implemented the same system using Vuforia and video see through tablet, as well as using HoloLens. And we again find that the HoloLens was less preferred or showing higher cognitive load compared to a touchscreen device. And in conclusion, we can say that these three applications, just a limited set of applications where we use this our theories of cognitive load estimations along with other parameters. But it is very important to note that the findings will be dependent on sensor. For example, as I just mentioned, that the HoloLens eye tracker has different specification than the Tobii eye tracker used in video see-through and VR interface. Similarly, users are more accustomed with touchscreen interface, so that may not be the best control strategy. But saying so, we also noted different EEG response on the electrodes at the optical cortex whenever we are switching from mixed or augmented reality to virtual reality, which can be further investigated. And what we can consider as a takeaway point from the whole presentation, that we can consider is one of many theories of cognitive load estimation. This may not be the best or the only techniques, but this is a technique where we can use portable instruments like the EEG cap or eye gaze tracker, and we apply the same techniques for a plethora of applications. At the beginning of the presentation also I showed some flight simulator or spacecraft simulator applications, and it can give you one of the means to compare different extended reality systems. Of course, should not be used as the only means. It should be considered in accordance with other parameters, like more direct parameters like users direct feedback or task completion time, safety, etc. But still, at the end of the day, that we present a way with some theoretical background that can reliably used as a technique to compare different extended reality system with respect to cognitive load estimation. So with that, I will finish this presentation, and thanks everyone for your patience. Thank you.